For today's video, first video for the unit, we're going to be introducing this concept called the solution. And so this is really what a lot of the chemistry is going to look like for us for the remainder of the year, where we have two substances that are evenly, thoroughly mixed together, which is the true definition of a solution. And there's a couple of terms that are associated with that, and they're kind of all connected through terminology. Solute is the substance that's being dissolved, and a solvent is the substance that's doing the dissolving. So we're going to be taking chemicals like sodium chloride or sugar, and instead of reacting them as a solid, which we know them to be at room temperature, we're going to dissolve them into water, which opens up their surface area and allows a chemical reaction to proceed a lot better, right? So the one other part of this that I really want to emphasize is this concept or the term thoroughly, right? For a true solution, when you have a solid and a liquid mixed together, every single minute detail of that new solution has the equal amounts of the chemical that you dissolved into it. All right, so there are some things that we know don't dissolve in water, like sand. And if I were to pour sand into a beaker of water, it would just rest at the bottom and be a really wet, lumpy mess. All right, but something like salt and sugar that we know to dissolve in water very easily will cause some kind of a thorough mixing so that the top few milliliters of this solution and the bottom few milliliters of the solution have again the same amount of solute. They're thoroughly mixed. The example and one of the things that we're going to be utilizing in this unit to really support this idea that I always use is Kool-Aid. When you make a pitcher of Kool-Aid, you want the first sip and the last sip to taste the same. You wouldn't want the last sip to have most of the flavor and the first few sips to be just watered down. Okay. So if we look at something like sodium chloride, which I'll write just a little bit larger, we notice that there's multiple different atoms that are broken up into solution. We've got these green and these blue atoms. And of course, these are like way zoomed in so that we can visualize this a little bit better. But this is the way an ionic compound that we have formed from a positive and a negative ion, that's the way that they're going to behave in solution. And we refer to that as an electrolyte solution because they conduct electricity. If you've ever drank Gatorade to replenish your electrolytes, that's essentially what you're trying to put back into your bloodstream because you sweat so much and got all of that sweat out of your system. All right. So the reason that we have an even or equal number of greens and blues is because that NaCl has one sodium for every one chlorine atom, right? Over here, we look at something like sugar, which has a molecular representation like C6H12O6. We don't have any metals. They're a covalent or a molecular compound. So while they dissolve, they still stay their really large molecule shape, but they break apart from each other and dissolve into solution. So when this happens, we refer to that as a non-electrolyte solution. So there's not positive and negative metal and non-metal ions like in this beaker to the left. Okay. So how would we illustrate something like a calcium chloride solution? Well, given the formula CaCl2, if we were to have this rectangle represent a beaker of that solution, because we have three total atoms within that formula, for every one calcium ion that dissolves, we're going to have two chloride ions that form. And so if we have a couple of molecules going into this solution, we would need something to stay in that same ratio. Okay, so for every one of these that dissolves, one calcium ion is going to form and two chloride ions are going to form. Okay, so we also have to understand that not everything is going to dissolve. And so there are certain rules for this concept that we call solubility, which just means is it going to dissolve into water? If it does, then we see it kind of disappear into solution, meaning it goes colorless or retains the color of the original chemical. And then if it's insoluble, it means that it won't dissolve in water and it behaves kind of like sand does. It'll just rest at the bottom of the beaker and won't fully dissolve. So we've got these two tables. The first one is our table for all things that are soluble. And then the second one is the table that are all things insoluble. And this is absolutely not something that you have to have memorized. This is on your periodic table. It's on the back. So you'll want to get your periodic table out for this set of video notes and just kind of review this information, right? So we read it by identifying the component on the left, right? So if it has nitrate, acetate, chlorate, or perchlorate, if it's a group 1, ammonium, if it has a halogen, or if it has a sulfate, all of these things are readily soluble, but there are a couple of exceptions over here, and we have to figure out if it follows that exception rule, which would then make it insoluble. And then on the second table, these are the most common insoluble components, and they're readily not going to dissolve into water unless we follow these exceptions, which make them soluble. All right, so it looks a lot busier and it looks a lot messier than what we actually see. Once we put it into practice, it's pretty straightforward. All right, so the first one we're going to talk about is NaCl, which is something that we know dissolves pretty regularly into water. All right, this is just table salt. It was the example at the top of the page. But I want you to try and identify what rules on these two tables make this, in fact, a soluble compound. Right, so we notice that there's not a whole lot that says sodium or chlorine, but we have to remember that this term, halogen, refers to group 7. So that's your fluorine, chlorine, bromine, and iodine, right? So essentially, any compound that has fluorine, chlorine, bromine, or iodine is going to be soluble unless they're bonded to lead, silver, or mercury. Right? The other thing that you'd want to notice is that the group 1 metals, those are lithium, sodium, potassium, rubidium, that first column. So if we have anything that contains lithium, sodium, potassium, and rubidium, again, they're going to be soluble. And for those, there's zero exceptions. So everything that has those compounds in it are soluble 100% of the time. So over here, we've got two rules that support this as, in fact, being a soluble compound. Okay? If we go on to the next set, we've got barium sulfate. And again, we'll notice that most of these tables are set up by the negative ions. So if we try and identify where sulfate is located, we've got the rule under the soluble table that most sulfates are soluble unless they're bonded to lead, mercury, barium, calcium, or strontium. And here we've got a sulfate bonded to barium. So then that means it's an exception, which makes it insoluble. Okay, so this would not dissolve into water, right? If we look at lithium carbonate, we again have our group 1 metal compounds that makes that soluble. And then down here, if we identify, we've got carbonates, which are in the insoluble table, but the exception to that is when a carbonate is bonded to a group 1 metal. Here, lithium is one of those group 1 metals. So lithium carbonate is, in fact, soluble. But again, if we've got barium carbonate, for that same rule, carbonates are insoluble. And the exception is, again, only group 1 metals and ammonium. So barium is not one of those exceptions. So this makes it an insoluble compound. Right, so if we go to sodium fluoride, again, we've got this halogen rule, and there's no sodium exception. And again, we've got that group 1 metal rule, and there's no exceptions for that. So sodium fluoride is going to be soluble. AgCl, following that halogen rule, again, chlorine is a halogen. This time, the exception to that is when silver is bonded to one of those four. So AgCl here would, in fact, be insoluble. And then for the last two, they both contain that OH hydroxide ion. And so hydroxides, again, are this really insoluble compound unless it's bonded with a group 1 metal, which it is here in sodium hydroxide. But if it's bonded to this iron 3 ion, that's not part of the exception rule, so then it still stays insoluble. So sodium hydroxide will be soluble. Iron 3 hydroxide will be insoluble. Okay, so the solubility affects how those ions are going to break apart into solution and affects how the chemical reaction is going to proceed. For compounds that dissolve into water, we have a way for us to visualize how much we can actually dissolve. Okay, and then the other example that I go to is back to the Kool-Aid reference. It is possible to add too much Kool-Aid powder because eventually it just turns into like a solid gloopy mess. So there's a point where you have too much solute and we do what's called a supersaturation. We've added too much so that it can't dissolve. So a solubility graph, like we have to the right, is an illustration that shows how much solute can exist per 100 grams of water. Right? So you don't have to have any kind of like this graph visualized or memorized. You'll be provided with this reference point, but we need to be able to identify the components of it. So on our y-axis, we have the solubility of our solute, which here happens to be sodium acetate, right? And that's per 100 grams of water. And then down here, we've got a temperature, which shows us that as we increase the temperature of our water, we're actually able to dissolve more of our solute into the solution, right? If the amount that we add is under this line, then we say that it's unsaturated, which means we have too little solute and more can be dissolved. If we're exactly on this line, then we've reached that perfect ratio, the perfect amount of solute dissolved into solution. And if we're above the line, again, it's that Kool-Aid example where we've added in too much solute and most of it won't dissolve, we would need to either heat it up or add more water or add more solvent to reach that solute to solvent ratio. Okay? So again, above the line, too much dissolved. Below the line, too little dissolved. Right on the line is that perfect amount. We don't want to add two more. We couldn't add any less. Right? So let's take a few practice problems. We got 3 down below here. And then if you want to read through those and using the graph above, try and visualize what the correct answer would be. All right, so for the first question, it says if 50 grams of sodium acetate is dissolved into 100 grams of water, the solution is said to be blank. So we have 50 grams. So we got 10, 20, 30, 40. Here's our 50 line. Dissolved into 100 grams of water. And for all temperatures at this 50 gram mark, no matter what temperature we're at, we're underneath this curve. So no matter what, our solution is said to be unsaturated. So even at our coldest temperature, we could still dissolve about 20 more grams of solute. And at our highest temperature, we could get all the way up to about 140 grams of solute. Right? At 75 degrees, so now at a specific temperature, how much sodium acetate can be dissolved to saturate the solution? So if we follow the y-axis up from 75 degrees, at this line is the point at which we're perfectly saturated. And if we travel across this x-axis, that's at 110, 120 grams of solute, right? And then if 100 grams of sodium acetate is dissolved into 200 grams of water, the solution is said to be what? Well, now we have to take into account the fact that we're adding a certain amount of solute per 100 grams of water. So if we have 200 grams of water, in 100 grams, we would only have 50 grams of sodium acetate dissolved. So we had 100 grams of solute per 200 grams of water. Our graph is referencing per 100 grams of water. So then we would only have 50 grams of solute per every 100 grams of water. So really question 3, although it doesn't look like it, is asking the same thing as question 1. If you have 50 grams per 100 grams of water or 100 grams of sodium acetate per 200 grams of water, regardless of what temperature you're at, again, our solution will be categorized as unsaturated.